Okay, welcome everyone to the afternoon session of the first day of Zoomplitudes. In this session, we have 5 great speakers. Before introducing the first one, let me remind you about the rules. So each talk will be 25 minutes long, plus 5 minutes for questions. Please remain muted during the talk. If you would like to ask a question, please raise your hand using the Zoom feature. You can also ask questions in the chat, and then I might read them out later on if there's time. Very good, ready? So our first speaker today is Yael Shadmi from Technion, who will tell us about on-shell standard model EFTs. Please take it away.
Thank you. Thanks, Sebastian. So you can hear me and see the screen okay?
That's right.
Okay, great. So thanks a lot for having me. This is super exciting because it's my very first Amplitudes meeting. And for this reason, I'm also very disappointed that this is the way it's taking place. It would have been really nice to meet people in person, but I'm very happy that this is taking place after all. So I'm going to be talking about on-shell standard model EFTs. And this is going to be based on work with Yaniv Weiss, Gauthier Durier, Tepe Kitahara, and also Camila Machado in some ongoing work. And as we heard not so long ago, there was this expectation or sense that the LHC would turn on, and shortly afterwards, we're going to have descending upon us the full UV Lagrangian of either the full MSSM or an RS model or composite Higgs model or what have you, and all our questions regarding electroweak symmetry breaking will be answered. Is there a dynamical origin for the Higgs Viv? What solves naturalness, and so on and so forth. Instead, we're still stuck in the deep infrared, and if we want to make progress on these questions, it's pretty clear that experiment will need to lead the way. And as a result, effective field theories have been the focus of a lot of attention because they offer a systematic framework for parameterizing our ignorance in going beyond the standard model. So we already had a great introduction to the subject by Nathaniel before the break, and so I'm gonna have to rely on that and refer to that a lot as we go on. So, of course, if we're interested in electroweak symmetry breaking, the particles that are the most interesting are the heavy ones, the Higgs, the W, the Z, and the top, because that's where we might get clues about electroweak symmetry breaking. So we already heard from Nathaniel about the various different effective field theories that people have been considering. The one that's been getting the most attention is the SMEFT. So here we assume the standard model fields and the full gauge symmetry of the standard model. And I want to remind you of the first basic steps, or the basic steps that you need to take in order to implement this program. So the very first thing you need to do is you need to write down the EFT Lagrangian. In other words, the thing that you need is a basis of independent operators. And in order to get that, you need to eliminate all sorts of field redefinitions coming from the equations of motions, integration by parts, and so on and so forth, which boils down to the problem of the Hilbert series for this problem. And at the level of dimension 6 operators, there are a number of bases that characterize the full set of dimension 6 operators. And in terms of the counting of operators, this problem was solved by Henning and company to any dimension, basically. Just to give you an idea, when you come to dimension 8, it's only very recently, actually just during the past month, that we have a full construction of operators at dimension 8. Now, once you have the Lagrangian, the next thing you need to do is go to the broken phase and set the Higgs to its Viv. And once you do that, of course, all the standard model couplings get corrected by corrections of order V over lambda. And once you have that in hand, you can go ahead and compare to experiment and fit those couplings from some sources and determine the cross sections from that. So the goal in this talk is going to be to just go ahead and construct EFT amplitudes directly without resorting to Lagrangians. So maybe this is something that shouldn't be so hard to sell for this crowd, but let me give you a motivation in any case. So there are a number of reasons why this could be a good idea. The first one is that the EFT program that we've heard about is mostly bottom-up. So you start with the standard model fields, perhaps with an additional new field X, and then Lorentz symmetry, global symmetries, and gauge symmetry determine the EFT Lagrangian. And in complete analogy, if you take a bootstrap approach to the construction of on-shell amplitudes, this also proceeds in a bottom-up way. So starting with the standard model particles, there's Lorentz symmetry, global symmetries, and of course, together with unitarity and locality, these dictate the structure of these on-shell amplitudes. Now you could impose the unbroken gauge symmetry, and if you didn't, it would have to emerge from the consistency of the theory, but everything is going to be determined up to some unknown coefficients that come with the contact terms, and these are the analogs of the Wilson coefficients. So the nice thing about this is that this whole issue of field redefinitions and gauge redundancies never show up because you're just dealing with on-shell quantities. Another nice thing is that you calculate physical observables directly that you can then relate to each other. And on the technical side, these EFT vertices or EFT operators usually give rise to vertices that are fairly complicated. They involve lots of fields and derivatives. And so you might hope that amplitude techniques would simplify calculation. But there's actually more to this program. And this is related to what we've heard before by Nathaniel. And so the point is that in the SMEFT, we assume the standard model field content and impose SU2 times U1 at the scale V. But you may want to take a more general approach and ask about other possibilities where SU2 times U1 is perhaps just realized non-linearly, or strongly coupled cases where strong coupling happens just somewhat above V, or multiple Higgs fields. And all of these ideas were highlighted recently. Actually, I'm not sure you can see my full screen. Let me try to get rid of that. Yeah, okay. So all of these different possibilities have been discussed in the literature for a long time, but were recently highlighted, essentially motivated by the Higgs couplings program. So as these people are argued, in order to get some indication for which one of these options is realized, one of the best diagnostics are processes with multiple Higgs or longitudinal vector legs, which can differentiate between these two possibilities. So, and in some cases, these processes give you better sensitivity to Higgs couplings themselves than processes that involve external Higgs legs. So from both these point of view, a bottom-up derivation of on-shell amplitudes is a good idea. First of all, you can be very model independent and capture these different possibilities. And in addition to that, if you want to look at processes with multiple legs, then you have a hope of getting expressions that are more compact and tractable, so that it would be easier to look at how to understand how to probe them. Okay, so my so the outline, what I'll do in the rest of this is I'll talk about some generalities that we'll need, and then as a very simple warm-up, I'm going to give you some example of the construction of an EFT amplitude in the standard model plus some new resonance, and then we're going to move and discuss the full standard model EFT. Okay, so this subject, of course, has a very long history, starting from a very general understanding of EFT amplitudes with online shifts and understanding their constructability, and going on to a very rich program of mapping EFTs in general. Especially interesting from the point of view of BSM is the soft bootstrap, which leads to the construction of nonlinear sigma models. And from the point of view of the standard model EFT, as we saw, there are many results that were beautifully explained via amplitudes, like these vanishing interferences and the vanishing operator mixings that Nathaniel talked about. But as I said, the approach we're going to take here is, you can say, just do it. Instead of deriving some properties of the Lagrangian from the amplitude program, we're directly going to derive the amplitudes. So what we're going to do is take the following input, the particles, namely their masses and spins, the global symmetries and charges, and the unbroken gauge symmetry. These together determine the 3-point amplitudes, and higher point amplitudes are then given by bootstrapping these together. And of course, the thing that's most relevant for us is the contact terms. These generically involve non-renormalizable couplings, and these are the analogs of the Wilson coefficients. So in terms of the different couplings that show up here, we have the couplings that appear in the 3-point amplitudes. These are mostly the renormalizable couplings, namely gauge and Yukawa in the case of the standard model, but also non-renormalizable couplings. And then we have these contact terms that give rise to more EFT non-renormalizable couplings. Now, a recurring theme here is going to be masses. I'll talk a lot about masses. And there are a few good reasons to think about them. So from the amplitude point of view, one thing that I want to stress is that although masses complicate lots of things, there are some things that they complicate, there are some things that they actually simplify. So that's one thing that we're going to see. Another one has to do with the EFT point of view. So if you think about the standard model, the EFT Lagrangian, it involves two sorts of expansions. One is the derivative expansion, which leads to an expansion in the invariance over lambda squared. And the other one is the Higgs expansion, namely an expansion in more and more Higgs fields that leads to a V over lambda expansion. And this leads to this geometric field space standard model EFT that Nathaniel was talking about. And when you work with physical on-shell amplitudes with physical massive particles, essentially what you're getting is that you automatically sum all of these orders and they're all encoded in your result right away. Another reason to think about masses is, of course, electroweak symmetry breaking. And this is a long shot, perhaps, but you might hope that we would get new insights by thinking in terms of on-shell amplitudes. And one very compelling idea in this respect is this thinking about Higgsing as an infrared unification of amplitudes that was discussed in this paper by Nima and collaborators. Okay, so the first thing we're going to need is these massive spinor variables to describe the amplitudes. And here the idea is to split the massive momentum into two light-like momenta. And then the momentum is written in terms of 4 spinors with indices, with the index I taking 2 indices. These spinors then transform under the SU2 little group, under the SU2 little group of the massive case. And we can convert between square and angle spinors with the momentum vector, which basically just amounts to the equation of motion. And an amplitude that involves some external particle of spin S comes with a factor with 2s of these external spinors with the little group indices symmetrized. So we're going to use the bold notation that was introduced here, where the little group indices are implicit and symmetrized. Okay, so let me give you a first example of an EFT amplitude that you might want to construct. So this is in the context of not just the standard model, but a standard model plus the addition of a new particle. So this can be relevant for LHC searches for new particles. For example, this guy can be heavy or light. And we're gonna calculate amplitudes that involve this new guy X and gluons. And what I want to show here is a very simple example where X is a spin 0 particle. So this is a singlet of SU3 times U1. You can even take it to be the Higgs. And here we have a very simple expression for the tree-level amplitude involving this guy and 3 gluons of positive helicities. And I'm showing this up to dimension 13, but it's completely trivial to go to higher dimensions. So there's, of course, the spin part, which is determined by the little group in this case. There's only one term that arises from in the factorizable part that comes from the gauge coupling times the coupling of X to 2 gluons. And then we have the rest of the bunch. So the main thing to take home from this is how simple this expression is and how Bose symmetry essentially dictates these polynomials and allows you to go to very high dimensions. You can do very similar things for a spin 1 resonance, for example, where this would be the leading amplitude and there's no factorizable part. Now, a byproduct for this is that this gives you a completely simple way of counting independent operators up to very high orders, if this is what you'd like to do. Okay, so let me now move to the electroweak theory, which is the main focus of this talk. So there are different approaches that you could take when you think about constructing electroweak amplitudes. One is to construct amplitudes involving massless particles in the unbroken phase. So that would give you a direct mapping to the SMEFT operators. And this was done in this paper, for example. Another one is to construct amplitudes with external legs that are the physical standard model particles, whether they're massless or massive. So here you can either impose SU2 times U1 at V or not impose this. And this is the main thing I'm gonna discuss today, namely take a completely purist approach and see what we get from the standard model particle content. So going back to this picture, our input here is the particles, the W, Z, Higgs, and so on and so forth. And the only symmetries we impose are electromagnetic charge and baryon and lepton number conservation. So these together determine the 3-point amplitudes, and then we can go on and construct the rest. So our main goal here is to construct the EFT in this case, but along the way, it's also interesting to ask how SU2 times U1 emerges, how the gauge symmetry emerges, and how the Higgs mechanism emerges in this case. How do we see, for example, the patterns that we know from the standard model picture of electroweak symmetry breaking? So there are different ways that you could do this. One completely bottom-up construction that you can, or one purely bottom-up way in which the standard model gauge symmetry can arise is by requiring perturbative unitarity. So looking at the high energy growth of the different amplitudes, we know that any bed high energy growth must be suppressed by the cutoff scale. This is something that we know, of course, since the 70s. The standard model is the unique theory with a standard model particle content that is unitary. And so requiring perturbative unitarity will give us relations between couplings and masses that we anticipate. Okay, so let me give you some examples of 3-point amplitudes. The first one I want to discuss is a fermion-fermion Z amplitude. So this is completely fixed by Lorentz, or the little group, to be given by this expression. There are 4 terms here. These couplings here are all dimensionless, and this lambda bar denotes the EFT scale in the broken phase. This actually contains all the helicity amplitudes by choosing different values for the little group indices that are implicit here. And there are 4 independent spinor structures that appear. Their number is simply determined here by angular momentum considerations. Now, how do we distinguish between renormalizable and non-renormalizable terms here? Well, we can look at their behavior in the high energy limit. And so these two scale is mz times the energy, whereas these two scale is the energy squared. And so we can live with an mz here in the denominator and still get good high energy behavior, whereas here we must have lambda bar appearing. So these indeed give rise to the gauge couplings, and these are the dipole terms. Okay, now if you wish, this is just the 3-point version of perturbative unitarity. If we were to square this 3-point amplitude in order to get a 4-point amplitude, then here any E squared must be suppressed by the cutoff lambda. And that tells you that any E squared in the 3-point function must be suppressed by lambda bar. So that's exactly what we see. Okay, now since this is a 3-point amplitude, there's no kinematics. I mean, the kinematics is completely trivial. The different invariants are given just by the masses here. So this is a full result. Of course, if we wanted to match it to a computation from an EFT Lagrangian, then this result essentially sums all the orders in perturbation theory, but also, as we said before, all the orders in the V over lambda expansion. Okay, so let's take a break from EFTs and pause to relearn some things that we know about Higgsing. So there are many things that you can learn about the Higgs mechanism by considering the high energy limit of this amplitude. I'm not going to go through all of them, but just highlight one. So suppose we look at high energies. So mz over E goes to 0, and consider this particular helicity amplitude. That's the way it scales in this high energy limit. So you see that since we have mz here in the denominator, either this factor needs to go to 0 or this factor needs to go to 0. So if GL equals GR, we have a vector like fermion with no constraint. However, if these two couplings are not the same and we have a chiral fermion, then we see that the fermion mass better go to 0 at least as fast as the vector mass. So the fermion mass has the same origin as the vector mass. So that's precisely what we expect from the Higgs mechanism. Okay, another example that I want to highlight is the Wwz amplitude. So that's central to the non-abelian gauge interaction, which is why it's interesting. So for simplicity, I want to neglect the mass difference between the Z and the W and take them to be degenerate. In this case, this is the result for the amplitude. We have these 3 different structures appear. And the thing to notice here is that each one of these separately is completely anti-symmetric under exchange of 1, 2, or 3. So we see immediately that it's got to be anti-symmetric in A, B, and C. So the only thing that can appear here is epsilon ABC, and we see the SU2 emerge. So if we have 3 degenerate spin 1 particles, Lorentz symmetry basically tells us that we're seeing an SU2. So you see that compared to the massless case, this is even simpler in some sense, because the 1, 2, and 3 here are on completely equal footing. They all appear in the same manner, as opposed to the expression that we have in the massless case. And another thing that you see is that the masses are nice because they smooth the 3-point kinematics. So instead of the singular 3-point kinematics that we have in the massless case, here we have a much nicer expression. Okay. So let's move on to 4-point amplitudes. And again, discuss one example, the fermion-fermion Z Higgs amplitude. So in this case, Lorentz, and again, the little group, completely fixes the allowed spinor structures that can appear. There are 12 independent of those in this case. So I list them here, and they're also the ones related by parity. And any other structure with the correct little group transformation can be spanned by these, with the coefficients being polynomials or rational functions of the SIJs. So for example, here's another structure with the same little group transformations, and it can be written in this way. So this is the non-factorizable part of the amplitude. These are the two structures that we have a dimension 6, 3 a dimension 7, and this other one a dimension 8. And these different coefficients are given again as expansions in the SIJs of this form. And again, this result captures all orders in the V over lambda expansion. Okay, the factorizable part is given by gluing together these 3-point amplitudes, working to the leading order in the EFT expansion. You keep just one non-renormalizable vertex on each side, or I mean, just one non-renormalizable vertex in total. I'm not going to show the full result here, but I want to make 2 comments about it. The first has to do with masses again. So in some sense, again, masses simplify this factorization, because in the case of non-degenerate masses or broken symmetry, or simply the distinct particles that we have here, we have a separation of poles. So different factorization channels have poles not at the origin, but at different locations. Another thing that I want to come back to is perturbative unitarity. So looking at the high energy growth of this amplitude, again, there is a term that goes like the energy, and therefore we know that it's got to vanish up to corrections of order m over lambda. So we see essentially almost the same combination that we saw before. Either this difference of couplings needs to vanish, in which case we would have a vector-like fermion. But if the fermion is not vector-like, then this other combination of couplings needs to vanish, which tells us that the fermion mass is given by the Yukawa coupling times mz over the gauge coupling. So the fermion mass is completely consistent with what we know about the Higgs mechanism. Okay, so
Yael,
what we really,
in a minute or so?
excuse me?
Could you wrap it up in a minute?
Yeah. So what we want to do, of course, is to go towards the full on-shell electroweak theory with a full set of 4-point amplitudes and then higher point amplitudes. There's been quite a lot of work on massless amplitudes and basis for those that I'm going to go through very quickly. I wanted to highlight the systematic classification of all the possible terms that can go into these. And ultimately, the thing that we want to do is find basis for massive amplitudes, where the thing one needs to do is find those lists of independent kinematic structures that appear here. And it turns out that there are various ways to do that, and some of them are quite simple. Okay, so let me go on to the conclusions. We're interested mainly in the origin of electroweak symmetry breaking. The LHC is going to supply lots of data over the next decade, and EFTs provide a systematic way of handling the data. And they provide also the very first step in going beyond the standard model. So when you think about going beyond the standard model, there's the question of which standard model. What do you mean by the standard model? Do you mean the standard model Lagrangian? Do you mean the set of particles and interactions? And as I try to convince you, starting on shell introduces many simplifications and allows you to explore general UV theories in a way that's truly model independent. So ultimately, we can hope to learn about the origin of electroweak symmetry breaking. And the message here is that I think there's a lot of room for progress from amplitude experts, and masses are something that should not be shunned. They have many simplifying aspects, and they're, after all, the key to electroweak symmetry breaking. So I'll end here, and thank you very much.
Very good. Let's thank Yael. Questions. We have time for maybe one quick question.
Yeah, I want to ask a question.
Please.
Yeah, hey, I'm Abhishek from Duke. So you showed initially in the beginning, like how you started constructing these on-shell methods by starting from these Lorentz symmetry and global symmetry taken into account. It's a naive question. So how do you think if you want to use these on-shell methods, let's say to describe something like non-relativistic effective theories like NRQCD, how difficult would this approach be? Like in NRQCD, you would have to worry about Galilean symmetry instead of the Lorentz symmetry. So how difficult would be for on-shell? Can you unmute the phone? I can't hear.
Am I? Okay, can you hear me?
Yes.
Yeah, I can hear you now.
Okay. Yeah, so I think it's a very interesting question, and I think it's something that can be done. I mean, you should just use the symmetry of, you should just use the available symmetry in that case, and I think it's very interesting, and I think it's something that can be done, although it's not something that I personally have thought about, but there's no reason why you would not be able to do that. Okay,
but just to confirm with you, so the on-shell amplitude can now handle masses type of thing, like particle with masses. I think that's what the impression I got.
Okay. Yeah. You can handle particles with masses, and in fact, people have handled particles with masses in on-shell amplitudes for decades using different techniques. I mean, most of them rely on splitting the massive momentum into two light-like momenta. And then there are different formalisms based on that. I think a very nice, this formalism that I was describing that was introduced in this paper by Nima and Huang and Huang from 2017, that's a very nice and simple formalism to use, and that's what we've been using.
Okay, thank you.
Cheshan, did you have a question?
Oh no, I just want to make a quick comment regarding NRQCD, because like tomorrow we'll have the gravitational wave section, and that's literally trying to apply amplitude method to the non-relativistic gravity to the NRGR case. So it's not exactly NRQCD, but it's very similar. Thank you.
Okay, thank you. So let's thank Yael once again. Thank you.